All right, guys, in this video, I'd like to introduce you to a process that's called implicit differentiation. And this is a process that we use to find derivatives, as we've been doing, of relations with x's and y's, kind of all hanging out together, for which y is not an explicitly defined function of x. So for example, we have this relation that I use Desmos to graph, and it's xy squared minus x cubed y equals 6. That's something you've probably never seen before, and quite frankly, neither have I, but it looks pretty cool. The reality, however, is that these implicitly defined relation, non-functions, have derivatives, and they have slopes that are defined at most, if not all, of their points. We'll talk more about differentiability in another video. But for now, we're going to look at a process called implicit differentiation that we can use to find derivatives for implicitly defined non-functions or relations. So the first step, the process, is we're going to differentiate both sides with respect to x. Okay? So for example, when I'm looking at xy squared minus x cubed y equals 6. What I'm going to do is I'm going to take, with respect to x, the derivative of the left side, everything, and the derivative of the right side. Note that this is not y equals some function of x. It's not an explicitly defined function. Okay. Now I'm going to go ahead with the rules, right? So my rules, I'm going to take the derivative. Derive. Okay. And there's a little asterisk here, and I'll point it out when we get there. I have to use a product rule here, right? All the normal rules apply. So I'm saying to myself, okay, self, remember the derivative of product is f prime g plus fg prime. So I'm saying, okay, the derivative of x is 1 with respect to x times y squared plus x times the derivative of y squared. Now, when I differentiate y squared with respect to x, since y is not an x, the variable to which I'm differentiating, I have to treat y like an inner function, and I have to use a chain rule. So therefore, the derivative of y squared with respect to x is not just 2y, it's going to be 2y times dy dx, or y prime. Okay? So when we come to a y term, we treat that like an inner function and chain rule it. There's a times y prime at the end by the chain rule. Here's my chain rule step. Okay. You'll see it happen here again when I differentiate the second product. Again, it's another product, x cubed y. I'm going to say, okay, I'm going to take the derivative with respect to x of x cubed. Well, that's pretty easy. 3x squared times regular old y plus, now I'm going to take x cubed times the derivative of y. Now, the derivative of y with respect to x isn't just 1. It's 1 times, by the chain rule, dy dx. And we can be a little lazy if you want. We can call those dy dx y primes. Okay? And now I'm going to say, okay, the derivative of, let me move my ugly mugshot out of the way. Now I'm going to take the derivative of that 6 on the right side, and I get 0. Okay? So here is what we call our now derived relation. Okay? It's an implicitly defined relation. I use an implicit differentiation to derive it. My third step now is I'm just going to solve for dy dx. Think of dy dx or y prime as a variable for which I can now solve. Okay, so now I'm going to say, okay, I'm going to clean this up a little bit, as clean as I can write, which isn't that clean. I'm going to say, okay, that's the same thing as y squared plus, I'm going to call this term 2xy times, I'm going to call that y prime, same thing. So I'm just being a little lazier now because I have messy handwriting as it is. I'm just going to call dy dx y prime. Okay. Minus, now I'm going to distribute the negative sign. It's minus the whole product rule, which I already did. So it's going to be minus that 3x squared y minus that negative sign distributes x cubed y prime. I just renamed dy dx y prime, same thing. It's equals 0. Okay? And so now I'm going to solve algebraically. I'm in my third step for y prime, or dy dx. Same thing. Okay? The way that I do that is I just keep all the y prime containing terms. There's one of them. Here's another one on the left side. I'm going to factor out a y prime. So when I factor this out, I'm left with a 2xy. When I factor a y prime out of this term, I'm left with an x cubed. Equals, and now what I'm going to do is I'm going to get rid of these terms. Any term that does not have a y prime, I'm going to get on the other side. So those two red box terms, I'm going to move to the other side simply by using inverse operation. I'm going to add the 3x squared y, and I'm going to subtract the y squared. Okay, this is just a little algebra. Okay, and again, recall I'm solving for y prime. Right, here is my y prime, same thing as dy dx. So now all I have to do is I have to divide by what I'm multiplying y prime by. So the next step, I'm simply going to divide by 2xy minus x cubed. Divide by 2xy minus x cubed. And then I'll just rewrite it a little bit cleaner. So y prime, or dy dx, equals 3x squared y minus y squared all over 2xy minus x cubed. Okay? Now, that's a little bit different than what we've been finding as derivatives for explicitly defined functions, isn't it? Note that this derivative has an x and a y in it. Okay, therefore, if I'm trying to find the slope of a tangent line at any point on this crazy implicitly defined relation, which looks like a fun little graph, I have to plug the x and y value of the point I'm looking for. Okay. Also note that although it looks like we can clean this up, we really can't. There's no common factor in this numerator for all 4 terms. So it looks like we can start cleaning that ratio up, but we really can't. Okay. Now what I can do is if I go back to the graph, I say, okay, look at this point 1, 3. It appears as if there's a horizontal tangent, i.e. slope of 0. I can say, okay, let's show that there's a horizontal tangent, slope of 0, at the point 1, 3. So that's kind of cool. So now I can just plug in 1, 3 to my derivative. So at the point 1, 3, which is on this crazy implicitly defined relation curve, there appears to be a horizontal tangent, another slope of 0, instantaneous rate of change of 0. So all I'm going to do is plug in the derivative at the point 1, 3. I'm going to plug in a 1 for x and a 3 for y. And so I get 3 times 1 squared times y, which is 3, minus that y value squared. 3 squared is 9. I'll write as 3 squared for now. Over 2 times x, which is 1, times y, which is 3, minus x, which is 1 cubed. And what I notice is that I get, okay, I get 9 minus 9 up top, 0. Oh, good. And I get 6 minus 1 on the bottom, which is 5. Right? So therefore, I just showed using the derivative, which I got by using implicit differentiation. I plugged in the point 1, 3. This derivative requires us to plug in an x and a y value of the point of tangency. And I got 0, as I suspected from looking at the graph of that crazy little thing. Okay? So, to reiterate, here's the process for implicit differentiation. Okay? And this is a process to find derivatives for non-functions. Okay? Functions that are not explicitly y as a function of x. So these are more for relationships, deriving relations. Almost always, right? Y is not an explicit function of x. In fact, usually they're not even functions, period. So the first thing we do is we're going to take the derivative or differentiate both sides of the equation with respect to x. Okay? So whatever equation we have, okay, we start off with this crazy equation here, xy squared minus x cubed y equals 6. And I just derive both sides with respect to x. Okay. My next move is to just go about my derivative rules, right? Okay, so now I'm going to derive. Product rule, quotient rule, chain rule, okay? And as I'm deriving, here's where it gets a little different because I'm deriving sometimes y terms. So when we derive a y term with respect to x, we have to use a chain rule. So there's a times y prime. Right? Treat y like your inner function. Okay. And then, of course, our last step is to just solve algebraically for y prime or dy dx. Same thing. Okay, and that usually, if we have multiple dy dx's or y primes, that usually requires us to get all the y prime containing terms on one side, factor it out, and divide through. Okay, so there's your process for implicit differentiation. Hope this video was helpful. We'll clean it all up tomorrow. Bye-bye.